Hey everybody. So this is Monday's lesson, and we're kind of actually getting to the last little final stretch of material that we have in this whole course. So I'm kind of excited. So originally, we started with just studying functions, and then we kind of went to study inverse functions. All right. Now, once we did functions and inverse functions, we tiptoed into a special type of function called an exponential function. Now what we're going to do is look at another special type of function called a logarithmic function. Okay. Now, this has special relationships in so many ways to the exponential function, and you hopefully should start to kind of guess how it relates. There's a reason we studied inverse functions. So do you remember finding inverse functions? Hopefully you do. That was only last week. Let's find the inverse of an exponential function. So here is an exponential function. Remember how we find inverses? We would want to write that as a y equals 2x. And then what we would do is, remember, they just switch spots, the x and the y. What's that? Hang on, this should be a 2. And then we need to solve for y. But we don't know how to solve for y. We haven't done that in this course. We've solved for x's being down here. We've solved for x's being over here. We've never solved for a variable being in the exponent. And to tell you the truth, you actually don't have the ability to do this without a logarithmic function. You need this log function. Okay? The whole point of the log function is to solve for this y. Alright? So I will go ahead and spoil a little bit. This would be able to be rewritten as log base 2 input x is equal to y. That allows us to rewrite exponentials as logarithmic functions. Okay? So just as a way of practicing this idea a little bit more. So we're allowed to switch back and forth between these two, depending on which one of these we know and which one we don't. Okay? So first off, let me write them both side by side for easier comparison. So that you can kind of get the hang of switching back and forth. We'll practice switching back and forth in a second. First and foremost, remember this piece underneath the exponent's called the base. Well, if you write it in logarithmic form here as a logarithmic function, this piece that was the base over here stays the base. This is the base of the log. It's the thing that's kind of written as a subscript, kind of underneath the log or below, kind of, a little bit lower. So whatever was the base in the exponential function stays the base in the log, okay? And then look, these two guys, the input and what is it equal to, switch spots. So here the answer was x, and we input y. Here the answer is y, and we input x. So there's the solution. Notice it switches spots. There's the input into the function. Notice this time the input is an x. Input. So notice that the x and the y kind of change spots. So we go from a base 2 to a log base 2, and the x and the y, the exponent and the answer, switch places with the input and the answer, okay? So we just, as a way of practicing, let's practice switching back and forth a little bit with a few examples. The ones that actually have answers, so like log base 5 of 25 equals 2. That is a true statement. So can we write it as an exponential expression? Well, what's the base? The base is 5. So what's going to be the base of my exponent, 5? Well, let's see. The input is 25. The output is 2. Remember, when you do an inverse function, the inputs and outputs switch places. So the exponent, the input here will be the 2, and the output will be, what it's equal to will be 25. So the input and the output trade places, the input and the output. And the base stays the same base. So that's not too bad, right? I could even do fancier ones like log base 6 to the 1/6. It's going to equal -1. Could you rewrite that as an exponential function? Yeah, what's the base? The base is 6. This is the input, this is the output. They should switch places. So what's the input over here going to be? -1. What's the output going to be? 1/6. And notice, I told you these are true statements. That means these should be true also. Is 5 squared equal to 25? Yes. Is 6 to the -1 1/6? Yes. Alright, maybe one more. Could we switch the other direction? Could I go from 9 to the 3rd equals 729? The answer is yes, I can. I can switch that. What's the base? Let's write our logarithm. The base here is 9, so what's going to be the base of our log? 9. What's the input? 3. What's the output? 729. So switch them. What's the input here? 729. What's the output? What's the answer going to be? 3. And this happens to be a true statement as well. Okay, so we can switch back and forth. So now let's actually use, because none of us think in terms of logarithms. It's just not a natural way. We think in terms of exponentials. So I'll go ahead and tell you the way to solve things dealing with logarithmic functions. At least, excuse me, I'm kind of sleepy. At least on this basic level where we're looking at in this lesson, the easiest way to solve something is to rewrite it into something we can understand and try to make sense of. So let's solve for y. So look at this. Oh, it messed it up. That's my base 4. It changed the script here. Log base 4 of 16. Well, let's think about this. Let's rewrite it so we can find what x is. What's the base? 4. What's the input? 16. What's the output? X. Input and output switch. So 4 to the x equals 16. Think about it. Without having to know how to solve this, you could guess and check, or you should understand 4 to the what power gives us 16? Oh yeah, whenever that x is 2, whenever it's 4 squared, that equals 16, right? You could reason through that. Or you could do the techniques you learned in the exponential chapters, where you try to rewrite this as a base of 4. What could I rewrite 16 as? 4 squared. Well then, if the bases are equal, the exponents are equal. That's just from a few sections ago. Look at this one. Let's rewrite it so that we get the base is 9. Like I said, sorry for the formatting messing up here. Inputs 3, outputs x. Let's switch them. Inputs x, outputs 3. What would I need to do here? This one's a little bit trickier if you don't remember this. But I could square root 9 and it would give me 3, right? Oh yeah, that's right. Square root 9. How do I represent square root as an exponent? Remember, it's a fractional exponent. So x here needs to equal 1/2. If you don't remember this, it's because if I do something to the 1/2 power, that's the same thing as taking a square root, which is equal to 3, right? Okay, awesome. All right. A few more. And so the trick for all of these is just to rewrite it in this exponential form. The base is 3. Input's 27. And the output was x. So remember, the input and the output switch. 3 to what power will give you 27? Oh, I know what that is. It's 3 to the 3rd power. So x has got to be equal to 3. So if you can rewrite it as an exponential equation, you should be able to reason through or use things that we have learned earlier to solve it. So let's do one where the x is in a different spot. Okay, x is in a different spot. X is the input this time. The base is 5. Let's rewrite it. Base is 5. X and 3 are going to switch places. So the input will be 3. The output is x. Well, this one's not even a solve. What's 5 to the third power? This should be really easy. 5 to the third power, if you check it in a calculator, is 125. So what's x equal to? 125. Really easy. This time I put x in the base. So notice I'm trying x in all three spots as the output, the input, and the base. So let's rewrite this one. Maybe we can do this one. What's the base? X. There's the input and output. They will switch places. So x squared equals 25. Oh yeah, we know how to solve this. Wouldn't I just square root both sides? And that's going to give you what? That'll give you x equals 5. Now I have a question. Remember just last chapter we solved that, or 2 chapters ago we would say positive 5 and negative 5. Square root of 25, we would say, oh yeah, that's going to give us negative 5. But we have to be careful with negatives because logarithms can only deal with positive bases here, positive inputs here, okay, the x's and things. So for this one, the log really can't take a negative there. So we're just going to answer with the principal square root, just the positive 5. Okay? So awesome. So that's the meat of the lesson, is all focused on this ability to go from the log to the exponential. And then you can solve for x. If you can rewrite it, you can solve it at least these beginning ones. Okay? So now I want to show you three very basic properties that'll help us solve a little bit more complex ones, okay? Here, let's look at one at a time. The first property says if no matter what the base is, if the input is 1, we're going to get out 0. So let's do an example. Log, pick your favorite base. I'll do 4. Log base 4 of 1. I know that's going to equal 0, but let's pretend like we didn't know what it was going to equal. Okay? Well, if I rewrote this, it would be 4 to something equals 1. Oh yeah, isn't there an exponent that always spits out a value of 1? That's if the exponent is 0, because remember, anything to the 0th power is 1. Oh yeah, so any log that I take, no matter what the base is, if I input 1, I'm going to output 0. So this saves you the thinking as a property. You could memorize it, but it's not that hard to reason through that. Okay, let's look at the second property. Now, before I show you the second property, remember, we started with functions, and then we talked about inverse functions. And I told you that inverse functions had a special relationship. Or just when you switch the inputs and outputs of one, they gave you the inputs and outputs of the other, right? But remember, if you compose them or make a composite function where you stick one function inside the other, if those two functions are inverses, they just undo each other. Logarithmic functions, they are inverse functions with exponential functions. So if I take an exponential function and plug it into a logarithmic function, as long as they both have the same base, they will just undo each other. Or the other way around, if I take a logarithmic function and plug it into an exponential function, they will undo each other as long as the bases are the same. So look at this one. Log base anything. If I plug in an exponential function with the same base, this piece right here, the exponential base, well, let me get a different color so it shows up. The exponential function's base and the log in its base will just basically eliminate each other out, and you're left with whatever was sitting up here in the exponent. It just equals that. So for instance, log base, I don't know, 7. And if I put an exponential function in here like 7, or any exponent, 7 to the, well, it doesn't matter, 11. I know this is going to equal 11 because this base of this exponential and the base of the log are identical. So since I'm plugging them into each other, they just undo each other, and I'm left with that 11. Okay? Now this can work the other direction as well. All right? The other direction. If you have an exponential function where your exponent is a logarithmic function, if they have the same basis, they just undo each other, and you're just left with whatever the input was. So for instance, it doesn't matter, 3 to some power, but if that power happens to be a log with the same base as the exponent, someone give me a number, 6. I know that this is going to output 6 because this log base 3 and this the base of this exponent 3 undo each other because these bases are the same. So I'm just left with the 6. So that's just from the property, the fact that they are inverse functions of one another, and if you make a composite function, they will unravel each other. Okay. So one more topic, and we're done with this. We do want to talk about graphing these things. Okay. But pretty much everything we've done, really everything, most of everything we've done since you get out of all the funny line stuff in algebra to here, we're saying, look, let's just make an XY table to graph with. Okay. Now this is a little bit difficult to think about, so let's actually rewrite it just like everything else we've done. We're going to rewrite it in exponential. So what's the base? The base is 2. And so the x and the y switch places. 2 to the y equals x. Okay, now we'll tell you, you may want to write this down in your notes in your margin. When we do these, we rewrite it as an exponential, but I'm actually going to pick the y's because it'll be way easier to find the x as opposed to picking the x's and finding the y's. That would take a lot of effort. Okay, so let's actually pick some y values. Let's see. 0 should be easy. 1, 2. This should all be pretty easy. And then let's pick a negative y value just to see what will happen if I'm allowed to have a negative y. Go ahead and tell you I'm allowed to have negative y's, but I can't input negative x values. Okay, you'll see once you see the graph how this looks. All right. So if I put a 0 in there, 2 to the 0 equals, well, what's anything to the 0th power? 1. So every logarithmic function will have this 1, 0 point. 1, 0. If I put a 1 in there, 2 to the 1. Well, anything to the 1 is just itself. 2. So I got 1, 2, or 2, 1. So 1, 2, 1. If I put a 2 in there, 2 to the 2. Let's see, 2 squared is 4. So that gives me a 4. So I got the point 4, 2. 2, 3, 4, 1, 2. Heck, we could do another one. We could put a 3 in there for fun. And 2 to the 3. That'll give me a 9 coming out. So what is that? 9, 1, 2, 3. Alright, let's look at the negative one. 2 to the negative 1. Remember, that's 1 over 2 to the 1. Remember, you fix the negative by moving it down. Well, what's 2? That's just 1/2, right? 1/2. And you could do more negatives. 1/2, negative 1. What you're going to find is these are going to hug closer and closer, but never slip back past the y-axis here, because this is the inverse function of an exponential. Remember, an exponential has an asymptote at the x-axis. This is going to have an asymptote at the y-axis and never take a negative x value. It's only going to be able to take positives. It does not exist back here on this half of the graph, and it goes up this way. Now, this is very, very similar to the exponential functions. You remember the bases. If the base was larger than 1, it was an increasing function. And if the base was in between 0 and 1, like a half, was a decreasing function. And if you were to do that, I hope you're listening and not just watching with the sound off, so you're wondering what I'm drawing. But if I was to do something like log to the 1/2 x, that would almost be the same thing, but come through this way, flip it that way. Alright? Still have the asymptote at the y-axis, but it's a decreasing graph instead of an increasing graph. It would just flip it, but we don't really want to put that on there in case you're looking and it mess you up. Let me take it off. There. Okay? But that is another point, depending on what this base is, it could either be going up or going down. If this is a fraction in between 0 and 1, then you'll get this decreasing function going down. All right, awesome. That's all I have for you today. Make sure you do your worksheet. It'll be attached with the answer key. We're getting close to our final test. I'll email you more about that later. Make sure you're watching the videos and preparing. I hope you guys had a wonderful Easter. I will see y'all, talk to y'all on Wednesday.